is another problem to serve as an example for both class 7 and 8. It's a long problem. I'm not going to work through it by hand. Is that true? I think so. I think what I'm going to do is narrate from the solution manual, which I have modified. So, because there is some difference between what I've recommended that we do compared to what this solution manual would do. So, we have a spurred gear, pinion and gear pair with a diametral pitch of 12 teeth per inch. They're milled teeth, and so they have 17 and 30. And they have 17 and 30 teeth, respectively. 20-degree pressure angle, face width of 7/8, 0.875, and a pinion speed of 525 RPM. The tooth properties are ultimate strength 76 KSI, yield strength of 42 KSI, and a Brunel hardness number of 145. We want to use the Gerber criteria. We're going to use the Goodman criteria probably for one-way bending. For a design factor 2.25, what is the power rating of this gear set? So let me see. I'm going to pause it for a second and I'll be right back. Okay, so here is the problem, and I will try to annotate this and explain with the differences with their expectations and also where some certain things come from, right? So first off, we know from this problem that we have 17 and 30 teeth. So we look up right here from table 14.2, and we're able to find what the Lewis form factor is going to be for both of those, for the 17 teeth right here and the 30 teeth right there. From those, we also get the diameter of both the pinion and the gear by taking the number of teeth divided by the pitch, which is 12, right there. We get the pitch line velocity, V, from the pinion tooth diameter right here, and the RPM. So we get 194.8 feet per minute. And then we're going to go ahead and use equation 14.4b. For the dynamic factor, so it's a pretty low 1.162, and then for the endurance strength, right? So we want to try to get for fatigue. We're going to get the SE prime by taking 1/2 of the ultimate strength, which I think they told us in here was 76, and so we get that. Now we want to go through and go through the KA and the KB and that kind of thing right here. So for this, this is from the 10th edition, I believe. So they used we're using that 2.7, which I believe is for machine surface, right? We know that we're going to get something different from the 11th edition, but we'll stick with these 0.857 is what we get for KA. Now this is where there's some deviation. This is the method that they show in the example right here, so we're not going to do this part right here, right? So instead, and they're doing this to get the tooth thickness, I'm just going to take 1/2 of the circular pitch right there, and so all of a sudden my numbers are going to start being different. But that's, of course, that's going to be pi divided by the pitch divided by 2 right there. And so if you do that, I get 0.1, and I don't really like writing with this with the mouse right here, but 0.1309 inches is what I get right here. So there's the equivalent diameter right there. So I'm going to stick my tooth thickness in there of 0.1309 in here, and would I get the equivalent diameter of 0.2735 inches in mine. Okay. And so when I come and put this inside there, I actually get a number that's larger than 1, which is not typical. We usually typically will have some things, but I have 1.010 is what I have. And then I don't do this next part right here. All right, so this is they're using the Gerber thing from that example right there. Right, they went ahead and used this as the miscellaneous factor. I don't like using the miscellaneous factor. I also, by the way, we've already established that the KB was just slightly different. Right, it was 99. It was like 99.6%. On the other one, this is 101%, right? There's not that much difference right here. But anyway, what I end up getting here by getting rid of that 1.66 is I get a 32.57 KSI. Okay, so continuing on through here. Okay, so here's the radius of the fillet that they get, and we were told this information from example 14.2. So we get that 0.3 divided by the pitch, we get this, and then we take in R over D ratio here of here. But by the way, so I have a different one here. I have my 0.1309, right, is the tooth thickness here. So mine is a 0.191. And it's supposed to be a 9. Looks like a 9, yeah. So coming through here and using our D over D is infinity, but we use 3. Apparently 3 is equal to infinity. And if I look it up, I get about a 1.5 for my stress concentration from that figure. And I agree with this is a 0.62 with this fillet radius right there. And so, based on my 1.5 right here, my difference, I get 1.31 is my ratio right here. So some of the things that I'm going to do right here are going to be slightly different right here. So like I need to maybe break away from this piece right here, and what I say that I'm going to do, and maybe I'll write it out separately down here. I'm trying to save time, but I don't know if it's saving any time. But so what I had done, make sure that we say that the allowable stress is going to be 2 times the endurance strength times the ultimate strength divided by safety factor, ultimate strength plus endurance strength, and then put your KF right in there. So when I put in here for the for this, and I come up with, so I said it's going to be 2. Here's my 32.57, the endurance strength I found, 76. My safety factor was 2.25, and then I had 32.57 plus my 76, and then my 1.31, right? So all of that, and I got my allowable was 15.48 KSI, right? So coming back to what we had right here, and so instead of this right here, I get 15. Did I say 14? I think it was 14. I said 15.48 was my KSI. And they write PSI next to there, so they have a little typo, by the way. See that little typo they put in there? Okay. So I put that in there instead of what I had, and I think everything else here is the same. And so what I end up getting is 294.3 pounds. And so switching that out right here, putting that into the place, I find that I get 1.737 horsepower. All right, so that's going to be the limiting horsepower based on bending right here, I think. Is that true? Yes, right here. because I was using this equation right here, this the Lewis equation for bending, but just rearranging it, right, so to solve for our amount of force. So, but then now the next thing for the wear section on this, a lot of the things are going to be the same. One thing notable here is that they went ahead and they used Poisson's ratio for steel for both of the gears, right? And Poisson's ratio and the Young's modulus for both of the gears, and there's two of them right here because they were the same. So they got this elastic coefficient. They got 2,285 square root of psi. But if you go to the book right here, you can just look this up in the table 14.8 and you get, 2,300. Right, so there's 2,300 is what the value would be if you just looked it up in the book, and that seems like it'd be a lot easier, a lot more straightforward. Finding the radius of the curvature of each of the gear teeth profiles. Take the pinion diameter divided by 2, multiply by the sine. So we get these two, and then they went ahead, I don't know why, and they added them up so that they get a value right here. I don't know if they saved themselves any time by doing that. And then they also they used equation from chapter 6. They went and they used the Brinell hardness number that they got for the steel. Were we given that? I think. Yeah, 149. So they went ahead and they used that from chapter 6, this equation that they said, that's equation 668. And they found what the contact endurance strength is going to be. And then they went ahead and they used that square root. Did I change that at all? No, I went ahead and let them do that, where they're taking the square root of the safety factor. Let them, now, in this case, it's a design factor, right, because we're using it in this direction. And they said, okay, here is what the allowable contact stress is going to be. And if you look right here, they've rearranged. So they went ahead and they rearranged this equation right here. They rearranged this equation and they solved for this. They also went ahead and they put this in here as like one thing. So it's not quite obvious when they're doing that. So you can see here's the R over the R that they did up here that they stuck in there. But they rearranged the thing. You see that they squared this. So they get 22.6 pounds. And now you can see from the results that they took as part of this, that they get 0.133 horsepower, right? So now you do this comparison between the two things, and you can see 1.89 based on bending strength or bending fatigue, and then you get 0.133, so a lot smaller horsepower capacity. But that's like if you never want the thing to wear, right? If you want so if you never run the thing more than 0.133 horsepower, the teeth won't wear out, right? But that's just not going to happen, right? So you can see that things are much more sensitive to wear. So that was working through a separate example. I thought maybe that would be a useful thing. A lot of times I will. I never get to it in this class. The class is always too long, so I think it's good that I have it as I have it written out in this way. And I actually always post a solution to this. We'll often post the solution just for people to see. So I'll also do that in this case right here, so you can work through it. So there you go. 15 minutes, 14 minutes.